The RoboCup challenge was first held in 1997 with the motivation to progress research into robotics and AI, and continues to inspire and deliver state-of-the-art technology. These approaches can then be used in other robotics problems with the intention of advancing the field. As a result, the client has tasked Group 22 to produce a robot that conforms to a modified version of the F180 rules. Some key requirements include being fully autonomous, less than 180mm in diameter and 225 in height, compliant with the 80-20 rule, able to avoid static obstacles, and retrieve, dribble and score a goal, all while keeping to a budget of $165. The system was thus broken down in between the four of us, with Geordie on the vision, Jeremy on the drive, Emil on the kicker dribbler, and James on the AI. What you are about to see is undoubtedly the best performing kicker dribbler system ever created. After significant testing with 3 different dribbler materials, bar shapes and motors, you could say the final design is comparable to God creating Adam and Eve. This bad boy can exert substantial backspin on the ball using special synthetic rubber composite adhesives that give the impression like they were made to flick golf balls at high speeds. Designed at a height that will make the 80-20 rule essentially unbreakable, it's powered by a 6-volt motor running at optimal torque-speed ratio. The module is easily integratable, leaving room for a kicker to squeeze in underneath the bar. After consideration of various kicking mechanisms, the solenoid was chosen due to its quick reload and decent force. But in saying this, the design kicker could not be integrated into the final product. However, the dribbler was cleverly designed so that the polarity on the motor could be reversed with the handy L298 driver, now exerting front spin, which can launch a deadly 0.3 meter per second kick into the goal.
The vision system was created primarily using Python and OpenCV. Initially, frames are read from the Pi camera using multi-threading in order to improve I/O performance. We then take the frame and convert it to the HSV color space, where we can threshold the image to find the object we desire, in this case the ball. Here, a minimum enclosing circle is fit to the leftover blob, giving us an accurate reading of the position and size of the ball in frame. From here, we can get information about the ball in the real world using the properties of the circle. Similar methods are implemented for detecting the obstacles, goals, and walls. An alternative to this approach could have been to use machine learning, hode transform, or blob detection with edge detection. Some of these methods were implemented and proved inefficient, such as the hode transform for ball detection, and some of these methods weren't explored due to time constraints and complexity. Overall, we chose our given system for its ease of implementation, robustness, and speed.
The task of navigating around a field during a soccer robot match is incredibly complex, from avoiding obstacles to finding the ball. It's even a challenge to drive the robot towards the goal once it has the ball, as the robot needs to move in a certain way to minimize the risk of the ball spinning out. The navigational systems on this robot need to be able to react constantly to the changing environment and to make split-second decisions based on what's happening in the game around it. With the lack of location awareness, global positioning, the approach of reactive navigation was mainly used, in combination with a navigational strategy called potential fields. This means that the robot will decide how to react based upon what is and what was previously inside of its field of view. In our demonstration the other day with the client, we were able to successfully demonstrate the robot getting to the ball and then turning towards and facing the goal. As the robot now stands, it needs more work in integrating the complex custom-made navigational code structure that it uses into the rest of the onboard systems. This means that we need to test each module of navigational code, tweaking speed values, etc. until the robot is complete. Initial estimates place this at around 2 to 3 days of focused work.
An omnidirectional drive was chosen for the SoccerBot as it was originally intended to be able to strafe around obstacles. The Omni wheels have both a driven and passive rolling direction. A double Omni wheel design was chosen so that there was always a point of contact to the ground. 3 6-volt DC micrometal gearbox motors were chosen because they met the velocity thresholds in calculations and also accommodated for easier integration with the kicker dribbler system. 2 custom-made L298 motor drivers were used for controlling speed and direction of the wheels. The SoccerBot has a max velocity of approximately 26 cm per second and a minimum velocity of 6 cm per second. With the combination of these attributes, the SoccerBot is able to rotate and move in any direction.